Hi, I'm Robert Bolanos. I'm with Southwest Research Institute in San Antonio, Texas.
Hello, I'm Jorge Vega. I'm with Northrop Grumman and I'm a power electronics engineer.
And we're doing a video on how to compensate power supply using the average model that my mentor, Jack Alexander, taught me.
Roberto, can you explain to me how I can compensate a converter, say a buck converter? Do you have a model that you typically use? I'd like for you to walk me through how do I simulate this, walk me through the model that you would use, and how do I compensate it? How do I make it work correctly?
Okay, well, I'm going to go ahead and uh, show you how to do a flyback discontinuous, but the techniques will be exactly the same for a continuous conduction mode, forward or buck. Okay. So typically, if you're gonna compensate this continuous flyback, what I use a very simple model that Jack Alexander, who was my mentor, he taught me this real simple model. And basically, he used a voltage control current source. Okay, so it's voltage control current source. And typically, your current will be supplied here, and you have your output filter, and we can call this C load. And then your capacitor will have a equivalent series resistor. And you can have a series of these, but just to make the modeling simpler, we'll just go with one capacitor. And then you have your load. So this is basically your output filter, but sometimes they call it plant. Plant. Then once you have your plant, there's always a divider network, and that goes to ground. And we can call this R1 and R2. And this is really your feedback.
Hmm.
Then you're going to have an error app. And on the non-inverting, that's where you have a voltage reference, VREF, and it can be anywhere from 2.5 volts to 5 volts, but I've seen more 2.5 volts. And then from your inverting, that goes back to your feedback. So you're sampling your V out. This is V out, and then by a voltage divider, you're feeding some of the signal back in here. And the error amp compares this voltage, reference voltage, and you can think of the positive as the control. So basically, the op amp with feedback is going to force these two nodes to be equal. So if this is 2.5, this node with the feedback will be 2.5. And for it to be in 2.5, you have to have a certain uh,
Divider.
divider that will induce, let's say, 12 volts. And let's give this a value. Let's say that it's 24 ohms. So So 12 divided by 24, that means you're going to have 500 milliamps. So if you have 500 milliamps here, you're going to have 12 volts across that load. So once you have this, then this is what I call Jack's model, in that everything past the error app, this would be the error app. I'll just call it AO. The error app will have a capacitor, CINT, with a resistor, RINT. It's the integrator cap, INT, RINT, integrated cap. And they'll have another cap, C roll off. It's also known as high frequency uh, roll off. Okay, so once you have this, this is your compensation. These three components, the C roll off, C integrator, R integrator, is what sets your control loop. Then from here, the output of your error app, that is fed back to the input of the voltage control current source. So this model is a behavioral model. Okay, it's a behavior, or actually an average model. Okay, and this is valid for a DCM flyback. You can also use it for a CCM buck and CCM forward. Forward. Okay. Now keep in mind this is a first order model. It will not predict the right hand playing zero or the subharmonic oscillations. Okay. But it's simple enough that you can use it with these models, or these topologies, and you're able to compensate where it gives you enough information that you can set the control loop
Roberto,
accurately.
so this is if I'm doing current mode control, this is the model that I'm going to be
Oh,
using, right?
yes, that's right. Okay, so I'm I'm glad that you said that. So if your PWM, there's two versions. The first version that was invented was voltage mode. That was the first PWM that
Yeah.
was invented. And I think it was Bob Mamano or one of those guys. Now the second is current mode. So to use this model, if you're using a PWM that is voltage mode, then you use a voltage control voltage source. But if your PWM is a current mode, then you want to use a voltage control current source. So basically, if your PWM is a current mode, your output looks like a current source. That's basically the idea. And if it's voltage mode, then this is actually a voltage source. So that's the distinction. So in this case, since we're using a the, most people use current mode. And the reason you use current mode is because you get pulse by pulse, short circuit, short circuit protection.
Now, none of that is in this model.
No,
I'm not, I mean, this is a simple model that doesn't
yes,
include.
yeah, it won't do that.
Okay,
But the main reason that you use
current mode.
current mode, and that's what
Got it.
you should be using. Unless you have a noisy environment, then you use voltage mode. Okay, but for any other reason, you would use a current mode.
Very well.
And if you're going to use the current mode, then this is a model that you want to use. Okay, so now to compensate this, you got to go back and kind of do a little review of Bodhi. And we're going to start with the plant. And when I say plant, it's the output filter. Okay. So since we're using current mode, we can draw the current source. And you're going to draw your capacitor. And then you draw your ESR. And then you draw your R load. And then we put a ground here. R load,
Correct. Excuse me.
C load.
This image that you're drawing here is no different than this, right?
Yes,
This is exactly the same. You just
yes. So I'm taking little sections. Correct. I'm glad you pointed that out. So that this is this model. And if you do a spice model
yeah.
and you put a current source and you do a AC analysis, then you're going to get a plot that looks like this. This would be frequency, and then this would be your magnitude or the gain, right? So you'll have a certain amount of gain that comes out like this, and then at a certain frequency is going to start deflecting. Once you have a negative slope or deflects downward, that point is a pole. And that's easy to calculate. You can calculate as 2 pi C load times R load. So that determines that position or that reflection point. And then as you increase in frequency, then it starts going flat. So this is the second point of interest, and that would be your zero. And that can be calculated by 2 pi C load and ESR. Okay. Now, here's an important thing to remember. The slope of this, if you have a first order system, which is what this is, because there's no inductors here, so this is considered first order system, then this will have a slope of negative 20 dB per decade. And that's important. And then since this has no slope, it's 0 dB per decade. So if you do a simulation, current source, a current source with these two, this is what you're going to end up with a Bodhi. One question that you asked last time, how do we know what the gain is here? Okay, one way of knowing what this gain is, and I'm just going to go back.
Yeah.
Right now, I'm drawing this as an ideal uh,
Current source.
current source. But remember, we're using a voltage control uh, current source, and we have this input, right? And typically, the input you want 1 volt. You want to set it to 1 volt. And the reason we want to set it out that 1 volt is that your error amp, you want the output to be about 1 volt because inside the PWM, there's a comparator and there's a 1 volt zener. So you're kind of restricted to that range. Now, why is that important? Well, now I can calculate this gain. Since this is 1 volt, and remember, if this is, remember, we have 12 volts right there. So the gain is, that gain is 20 log, sorry, 20 log 12 volts divided by 1 volt. That will give you that gain. Make sense? You got 12 volts. Basically, if you put
Okay,
1 volt
yeah,
here,
yeah.
it's going to force 500 milliamps. That 500 milliamps will flow through here. And, and if you put 500 milliamps through this load, this will have 12 volts across it. So if this node is 12 and this is 1, well, that's your gain. Basically, you have a gain of 12. So that's what it is. It's a gain of 12. But if you do the math, okay, so the math, let me get my calculator. Okay, so let's go ahead and put this here. So 20 log of 12. Remember, it's 12 divided by 1. So you would have uh, a in dB terms, it would be 21.58 dB. So that would be that spot. That would be the gain.
Hey, Roberto, so the going back to this 1 volt,
Yeah,
right? I know that you use the controller from Unitrode. What controller is that?
yeah. Well,
You see,
yeah, you see 1845.
so that controller has, so if we look at the COM,
Mm-hmm.
if we look at the COM, it has a
Yes,
minimum and a maximum, right?
yeah. You you have the inside. There's an op amp, and typically, if you look, it says that it has a 5 volt reference,
Yeah.
right? So you're gonna have about 5 volts powering the op amp. And then if you look in the data sheet, it's got 2 diodes. And then it goes through a voltage divider network. This is 2R and this is R. So basically you divide by 3. So if this is uh, uh, 5 volts and of course it's probably not a rail to rail output. It probably maybe goes to 4.5, but you subtract 1.5, you get about what, 3.2 volts here, and then you divide it by 3, you end up right there, roughly around 1 volt.
Mm.
That goes to your comparator, the comparator, and it compares with the current. But the point is, right here, there's a zener, and you limit that to 1 volt. So this 1 volt is what we're restricting here. And we don't draw this, or at least in the model, because it's just
Yes,
easier to eliminate it and limit that to one volt.
Roberto. So what happens if I'm not using I use C1845? What happens if I use a different controller?
Well, then let's say if they have a different limit.
Yeah.
Let's say your CS. You look at the pin that says current sense, and if the limit is 1 volt, then that's what you want to set this voltage.
Yeah.
But if the CS is half a volt, then on your model you would set this to half a volt.
Oh, I understand. So I
Okay.
need to look at the data sheet then.
Yes,
And
you gotta, yes, if you want to mimic that
very
particular PWM.
okay, very
And
well.
you gotta remember also, well, we'll go back to the error app. There's another issue that I want to talk about that in about the reference volt, because the reference volts on some are 5 volts and some are 1.2 and some are 5 and 2.5. So that's that. So this is the plant or the output filter.
And then the other,
Yeah. And then The next set is the error amp. Okay. So the error amp, your non-inverting will have your reference. In this case, on the UC 1845, it's a 2.5 reference. And then you have your divider. And keep in mind, this is V out. And you're using a divider and you're feeding uh, a divided down or a scaled down voltage to your error or to the inverting side. And then you have that integrator capacitor and your integrator resistor. And then you have your high frequency cap. And I call it the roll off. Okay. So if you, let's say, were to connect a signal here, and then, and let's say you put a little sine wave, and you would use like the Bodhi 100, inject the signal in here, and then, or you could even use a function generator and put your scope here,
Got it.
right? And then monitor this. And if you were to monitor the gain of it and plot it, then you're gonna have a waveform that looks something like this. And then it flattens out, and then you have another slope. So basically, this will have a negative 20 dB per decade, and then of course it goes to 0 dB, and then it goes back to a negative 20 dB per decade. Okay, so this is a function because of the capacitor, the integrator, and at this particular point, it's deflecting upward. So that tells you that you have a zero, and you can calculate that by 2 pi C load times R load. I'm sorry, it's okay. Let me try to that point on the integrator is going to be 2 pi CINT, the integrator, times the R integrator. Okay. We're talking about here the error. So that point is what? Just want to make sure it's 1 divided by 2 pi R integrator and no C integrator and R integrator. Okay. And then the second point that you want to look is right there, the little hump. And if you notice, it flattens out and then it goes downward. And when you have a downward, that's a pole. And the equation for that is 2 pi C roll off and R integrator. Okay, so those are the two big points that you want to put check out. Now you might have a question. Well, what about this? This is the midpoint
Yeah. How do I
or
determine the
mid
gain?
band, mid band, and this will be this R integrator divided by R1.
Roberto, back.
Oh, hang on. And the reason is, see, this is kind of like a virtual ground. So this is zero, so this is zero. So in reality, it's a inverting. So it's this resistor divided by that. Because at that point, this capacitor is already, you can consider it as a short. the impedance is so low that this resistor and R1 dominates the gain during this time. And then once this resistor starts decreasing, this resistor will dominate, and this is what is dominating the impedance at this point. This is C roll off. It's dominant. This section is dominated by these two resistors, and then this is dominated by RINT, the integrator. Now, this graph, this plot, and putting together with the two other plots. Yeah. Okay. So now we're going to put everything together. So we're going to put the plant, and we're going to put the error amp together. Okay. Get it back down here. Okay. Okay. So we'll draw the body again. Okay. So this will be the plant, and this would be your hole of the filter, and then this will be your zero. And then what you want to do is you can't change your output filter. It's already set. And your output filter is set so you can satisfy your ripple requirement. Okay. So you have a certain amount of ripple that you're allowed. So that's already fixed. You can't do anything to it. Right.
How is the ripple related to this
Well,
here?
well, well, here, remember, it's the pole.
Mm.
So it's 2 pi
Our load C
C
out.
load and then R load. Okay. And typically, your ripple is a combination of two things. Okay. If you make C load very big, very big, very big, then the ESR will be the dominant. Okay, what do I mean by that? Okay, so if you have a capacitor and you have a ESR, you're measuring right there V ripple. Well, this ripple is a combination of this VC
I understand.
and then
Yeah.
this voltage, which is, you can say, ESR. And if you make this very big, you can think of it as a short. And if it's a short, then this voltage goes to zero, and then your ripple will be dominated by your ESR. And if this is big, then the ripple is actually ESR, the value of your ESR, times your current, your low delta ripple. Whatever you set that ripple, the current, that will determine your voltage. But the point is, this is already set. That's there, and the ESR is inherent in your uh,
Capacitors.
capacitors. That's here. So if you want small ripple, right, then you need. So if you want your ripple to be small, then your ESR has to be low. And if you want ESR low, then you need to parallel a bunch of capacitors. in series. So in this case, the, let's say, let's assume that they're all the same. The capacitors CL would be 3 since we have 3. So if they're 100, you have 300, 300. But the ESR divides by 3.
Oh, nice.
So makes it, you minimize that resistor.
And what that does too is that it pulls the zero out this way. Is that?
Yes, yes.
Yeah.
So that's the point, that this is kind of fixed to satisfy your voltage ripple. Okay. So what we can move or compensate, and just to make this a little easier, I'll draw points here. And what my Jack Alexander taught me was that you basically, you, if your filter has a pole, then you want to cancel it with a zero. So if you have a pole, then the error amp, you cancel it with a zero. And if you have a zero in your filter, and we'll do this, we'll say filter and then error amp, EO. Bring it down, EO. So if the filter has a pole, then you want your EO, your error amp, to have a zero. And if your filter has a zero, you want your error amp, you want to place a pole. Okay, so what do I mean by that? So in this case, remember we had that other drawing. Basically, we're going to duplicate this point, this. So now the error amp will go like this. And then remember, there's a upward inflection. That's a zero. So basically, pole, and you cancel with a zero. Okay. So now we want to cancel that. That means that we want to place a pole here. Okay. So this is the filter or the plant. And this is the EO or the error amp. Now, if you combine these, all you have to do is add the phases. So in this case, we know that this is 0 dB, or the slope rather, and this is negative 20 dB per decade. I'll just put 0 dB, and we all know that it should be per decade, and it should be negative dB, 0 dB, and then negative 20 dB. Okay, so now the loop is a combination of these two. So 0 plus a negative 20, you'll end up with a slope of negative 20 because the pole got canceled by this 0. And then in this section, you have this negative 20 dB slope, but then you have 0 dB. So the combination ends up with
-2.
negative 20 dB per decade. And then the last interval, which is this here, 0 dB plus a negative dB, you end up with negative 20 dB per decade. Okay, so that's the powerful technique that Jack uh, taught me, in that if you can cancel these, it makes compensation very, very easy. Okay, now it gets even easier. You don't have to calculate, these formulas. You can do time constant. Okay, what do you mean by that? When you talk about time constants, you should always think of R and a C. So in an output filter, you have this pole, your output filter pole, And so just we're gonna do well. If you do the RC and you calculate the pole, that means that you're gonna have C load and R load. Okay, so remember this is a pole, and we said that we want to cancel it with a zero,
Happy right here, right?
which would be this one, right? That zero is composed of C integrator and R integrator. And by canceling, that means that you want to make these equal, right? You want to make the cancel. So you end up with this equation. C load times R load is equal to C integrator R integrator. Okay. So so remember, this is the pole. That's the zero. This is set by your design. This is already set by your design. Can't do nothing about it. That's there. So now you have two variables. You can either set C or you can set R,
Yeah,
right?
Roberto, so
Uh-huh.
just to bring this back here,
Mm-hmm.
so I want to make C load
Yes.
and R load. Now, you said this is a pole, right? So I
Yes.
want to make
That's both.
this pole equal to this
Yes.
zero right here.
Yes.
Okay.
They're coupled.
So
Yes. They're yes. Exactly.
these are I'm gonna say a pair, and we want to
Yes.
cancel them. We're gonna get
Cancel
that.
each
We're
other.
gonna find time constant, just like you did here.
Yes.
I'm gonna make them equal to each other.
Yes.
And the end goal here is to find a value for him and a value
Yep.
for him, right?
Correct. So that's where this equation comes out. You can set your resistance first. Make it your first selection. You select a resistor. And what I do, I like to set it to whatever
10K?
well, whatever this resistor is.
Okay.
Whatever I set this resistor, I try to it's a starting point.
That's a good
Okay.
tip. So I want to make,
It's
so a starting point, I want to
yes.
make this equal to this.
Yes. Yeah.
Okay, I like
Okay.
that.
Just to start. So then once I know what my integrated resistor is, then it's then I just solve for the C integrator, and it's going to be C load, R load, R integrator, and that's it. This will make ensure that this zero is placed at the same frequency, and they should cancel out.
Okay.
Okay, so now yeah, right there. Okay, hopefully these are the equation. Okay, so now we do the same thing for that zero, and that's going to be C load times the ESR. Okay. And since we already know that they're supposed to be equal, we'll just say, and that's going to be C roll off. And remember, we already said RINT. Basically,
Mhm.
this zero, remember, this is a zero, and this is a pole. Okay. And we want to solve for C roll off. That'd be C load ESR and CRNT. Basically, you just need these two equations, and you can ensure that they get canceled.
Okay, so going back to the schematic then, just like you said, I'm gonna see if I can um I put it here for now.
Yeah.
So we have this, this, well, this here
Yes.
is going to be the zero,
Yes.
and this here is going to be the pole. And
Yes.
I need to make their time constants equal
Equal.
to each other.
Yes.
All right.
Yes.
Okay.
So
Right.
that's the beauty of if you graphically plot it, this is what you want, and you end up with a nice 20 dB. And generally, if you have a 20 dB slope, then you should have a well compensated supply. And usually, uh, as far as the figure of merit, phase margin. What do you use at your company? Is it like 60?
60.
Because
Yeah.
60 degree,
60.
yeah.
And you know what? I mean, see, at least for space
Uh-huh.
applications, right, which is where you are,
Mm-hmm.
there's going to be aging, there's going to be
Yeah,
temperature.
exactly.
The higher that we get without getting sluggish,
Yeah,
the better off we will be.
yeah, that's true.
We
And then for gain margin, it's about negative
can.
10, yeah, dB. So here's the target. If you can fit that, that's a good point. Anything 60 maybe or higher, anything negative 10 dB or lower, it just gives you a more slower a slower loop and yeah, basically a slower loop.
Hey, Roberto, so what happens if so I come up with the values, right?
Right.
And what happens if the bandwidth, the unity crossing
Oh,
is too low in frequency? Let's say that I landed at, I don't know, let's say, uh, 1 kilohertz. How do I make
yeah.
it? How do I make it? How do I increase it?
Oh, okay. So let's go back to this then. Okay. So basically,
So we want
you
to move the crossing over.
yes, yes, and you can do this by moving this gain up. So what controls? Remember we said that this is controlled by R integrator and then R1.
Yeah.
Okay. Then what you do is if you want to increase, let's say the bandwidth,
Say by 10.
and let's say you want to go 10 times or 1 decade, right? 10 times equals 1 decade. Then whatever your integrator resistor is, you multiply it times 10. So if you have a 10K times 10, then you make your resistor 100 kilo ohms.
Okay.
But remember, you want to keep the same time constant, right? So that means your integrator, if you multiply the resistor by 10, you have to divide by 10 to keep the same time constant.
So let's see if I got it. So I would multiply this resistance by 10,
10
and then I would divide this capacitor
by
by
10
10, and
by
I
10.
and I keep the same constant
Yes,
such that I can still cancel this
yes.
pole right here.
But if you remove this or divide this by 10, you also have to divide by 10 the roll off. And what it does, it'll shift the bandwidth by 10 degrees or by one decade.
Okay. Hey, let me see if I understood that right. So
Mhm.
if I'm going to multiply him by 10, so I divide
Multiply,
him by 10.
divide by 10, and you divide this by
And
10.
I also divide this by
It shifts everything.
so that so what happens then is that this whole graph shifts over
Well,
all the
these stay the same, but the bandwidth, the total comes up. And when it comes up, let's say it's right, let's say let's say this is the 0 dB right there. What it does this. See that?
okay.
So basically you have higher gain, it does this. So now instead of you're crossing right here. So this is so if you're crossing at 1 kilohertz and you raise the band, you'll cross at 10 kilohertz.
I understand.
That's what it does.
So let me put this picture that we talked about yesterday again, which is similar to the one that we had before.
Hmm.
Let's say that I wanted to fine tune this zero, move it out a little bit. Let's say that in the actual application, I needed to move it out just a tad.
Hmm.
In that case, I need to keep the same time
The
constant,
same
right?
thing constant. Yeah,
Okay.
yeah. So yeah, basically, if you do the cold zero cancellation, it just sets it makes compensating uh much easier. So this technique you can do it for a DCM, a discontinuous flyback. You can use it on a CCM buck to switch forward. So it's a good starting point. And like I said, it's a first order, but the technique of compensating up whole zeros applies to both.
Okay. Thank you very much, Roberto. I really appreciate it. Yeah. I mean, what I've understood is that here, right, I wanted to know the model. So here is the model.
Hmm.
You explained that this is a voltage controlled current source.
Current source, yes.
You went over the plant, you went over the air amplifier,
Hmm.
and it was nice how you explained how you bias this
Hmm.
by making this the gain that you need for the current that you
Yes,
will get.
exactly. Yes, and Spice, when you double click on the source, it'll ask you for the gain as far as and so if you want 500 milliamps here, you would set it at zero point 0.5 or put 500 M. So whatever current you want it to flow out, if this is one, then you set the gain to whatever your current, and that will ensure that it's biased correctly. It will converge, and you'll get a beautiful block.
Nice. And then this technique of cancellation, where we keep the time constants, we make the time constants equal, allows me to find C int, R int,
Yes.
C roll off,
Yep.
and and that's where I'm headed, right?
Yes. Yeah. So if anything else, and if you forget, if you if anything, just memorize these two equations, set your integrator, and if you use these two equations, which basically is your pole cancellation, then you're set. So just these two equations will be you'll be able to set your controller.
Thank you so much.
You're welcome.